All right, so we're going to get started with this will be chapter 8 in your books if you're actually looking at your books. And we're going to look at the nervous system in general, like its overall structure. We won't focus in on specifically, any sort of sense organ yet, but we'll just look at the general overall structure. It'll take us a couple of days to get through this. So first off, nerves. You have nerves all over your body. Nerves conduct signals throughout your body. Where are most of your nerves and nervous tissue located? In your head, in your brain, right? So your brain and your spinal cord collectively contain 99% of all of your neural tissue. Even though you have nerves, and they're drawn here with these big, thick green lines, yeah, those are where nerves are, but they're not nearly that thick, right? When you were cutting or working on your rats and dissecting those, did you see like big giant nerves running through it?
No.
Only if you cut off their head and saw their spinal cord. Otherwise, you did not see anything like that. You don't see nerves. They're incredibly, incredibly thin, yet they are all over the place. All right, so there is a lot there. It's just that this is not representative of how thick they are in their actual total volume or mass. But they are there. As we had mentioned or talked about earlier when we were talking about different types of tissue, one of your primary tissue types is neural tissue, and we had already talked about how neurons are our primary neural tissue cell. They are not the only type of neural cell. However, they are the primary signal sending cells. When you say neurons, you're talking about transmitting signals, and that's the whole purpose of your nervous system anyway. It is supported by neuroglia or secondary nerve cells that help support these. It's not just these, it's some of these other cells that help support it as well. Whenever we're looking at the structure of a neuron, we've talked about this before. You have this body of the cell with these branched areas. Those branched areas are called dendrites. Those are the areas that receive signals. They attach to other neurons. So you can see you can make multiple attachments with that one neuron. It then has a long sending end, which is the axon, and then terminates at the axon terminals where you have your synapses. That's where it actually releases the neurotransmitter to pass along the signal. Now, this looks all really boring, and maybe it kind of is, but this has implications for you. One of the interesting things about this is that this long part here on the axon is coated with a component called myelin. It's a fatty lipid component, and what that does is it actually speeds up the rate at which you can send a signal. So whenever that myelin starts to degrade, as it does in Alzheimer's, people are not able to effectively communicate signals in their brain. And if you've ever been around someone who has Alzheimer's or dementia, it's really hard because you see that person, lose the ability to kind of move some signals around. I think many of us probably have had relatives that have gone through that, or at least to some extent. And you kind of see them lose the ability, some of their cognitive function. And that's because this starts to degrade and they can't send signals from neuron to neuron either fast or effectively or efficiently. And sometimes that signal just doesn't get through at all. So that's actually a really unfortunate case of where that structure affects your function. And if that structure is degraded, it no longer lets it function. There's other degenerative nervous diseases that attack that myelin sheath and slow down nerve transmission, and will give dementia-like characteristics or symptoms, I guess. All right. You've got a lot of these, right? Your brain, which is the vast majority of your neural tissue, is a lot of these, and they're all interconnected, and they form these neural networks or pathways that help you be you and allow you to do all this stuff. So that's the general structure of a neuron. There's a few different setups for that, but that's basically it. Okay, we already talked about this too whenever we were discussing the muscle cells and motor neurons. We know that on here, when you're looking at a neuron, the sending end is the synapse, and it releases chemicals that then signal to the next muscle or neuron in the chain. What are those signaling chemicals called? Our specific one for muscles was acetylcholine, but in general they're called what? Neurotransmitters. ACH was our abbreviation, yeah. And so they release neurotransmitters, and then those transmit a signal or pass a signal along from one neuron to the next cell, whether that's another neuron or whatever, okay? Different neurotransmitters transmit different signals. Okay, now this is where it gets interesting. Once again, because this is how it functions, this is how it's built, things can happen to this that allow it not to work quite right? So this synaptic communication, we release our neurotransmitters from vesicles, they then release that chemical or molecule stimulates the receptor site, that then causes the dendrite of the next axon to pass along a signal, right? Now, what happens if that doesn't work quite right? Or better yet, what happens if you substitute some other chemical that can stimulate those exact same receptor sites? This is where we get into different drugs. So we're going to talk about drugs, finally, because some of you bring it up way too often. So this is actually how it works. So if you take a painkiller, how does it actually make things not hurt? I mean, some of you might have had, probably many of us have had our wisdom teeth removed or something, and they give you the shots in your mouth, and you can't feel anything, and so your face is numb, and you drool for a while, and you play it for all it's worth, and you're like, I really need some ice cream, Mom. Right? You totally, do that. Well, how does that actually work on a cellular level? Okay, what's happening is some of your natural transmitters, humans have figured out that other chemicals can mimic those transmitters or block the release of those transmitters long enough for you not to be able to send pain signals or whatever signal it is you're trying to send, and therefore you can use them as painkillers. So, for example, oddly enough, nicotine actually interacts with acetylcholine, and it actually will interfere or aid or influence learning and motor functions. Alcohol and barbiturates, which are sedative in nature, they actually mimic some different amino acids, GABA, which I'm not sure what that. I can almost remember what that means, but I can't remember right now. Anyway, that influences memory, learning, anxiety, coordination, right? So if anyone's ever had to been sedated whenever you go in to maybe get your teeth removed or some minor surgery, you might have actually stumbled around a bit like you were intoxicated almost as a result of that. Has anyone ever been with anyone? I have. I've picked them up from the little surgery or whatever, and they're like, they can't hardly stand, but that's a byproduct of those sort of things.
Like learning like you can't learn?
It influences learning, yes. You're not going to remember stuff maybe if you are under the effects of alcohol or something like that. Okay? All of your narcotics, like cocaine and things like that, they influence dopamine and serotonin, which do with the pleasure reward. This is why people get addicted to this, and it only takes a small amount. Things like cocaine and amphetamines, we've all probably heard all the stories and everything. You cannot win against them. Like some people it'll be cool. Well, no, it never is. Because at a very, very fundamental level, the way you send signals in your body, this interferes with that, and it starts to send other signals. And that pleasure, reward, craving, all that stuff gets influenced by that. And it's extremely addictive as a result, is because it can bond or block or mimic those receptor sites from like cocaine, like people say that cocaine's really great. I mean, they really like it. There's a reason they do it. But the problem with that is that's the only thing that's ever going to satisfy them once they get started down that road. We've all probably seen some people who had abused amphetamines or it was starting to control their life, and it doesn't take much for that to start to run people's lives. And really the human, willpower has nothing to do with it. At some point it becomes a purely physical type of addiction. And we see that where people go into opiate withdrawal syndromes, they get really sick, they have some major problems withdrawing from it. It has chemically altered how they think, right? That's why it's such a bad thing. Not that these inherently are bad, because some of these things are used to treat certain things. For example, cocaine is actually a kind of a sedative and a painkiller. I mean, they used to use it for that. Derivatives of that we still use, like morphine is an opiate, right? If any of you have ever had a major surgery, you may have had to take some sort of painkiller. And it might have been like that, I'm really glad I had that type of thing. But the problem with those, as always, is what if you become dependent on it? And that's been a big deal in our society. And it's going to continue to be. The beta endorphins, like beta blockers, which a lot of those opioids are, they make really good painkillers. Morphine is a great painkiller, but it's super addictive. So there's always these trade-offs when you start looking at these sort of messing with those natural transmitters, right? Do you guys have any thoughts on that? I mean, the reason they work the way they do is they either block the release of a neurotransmitter, they mimic a neurotransmitter and just don't go away, and they just keep on pushing that button type of thing, or they make the neurotransmitter, once it's released, not get broken down. One way or the other, it inherently changes how you're sending signals, and nobody is immune to that. It will eventually, sooner rather than later, start to rewrite your brain and how you send signals.
So you're still in pain, you just can't, you're not
those signals are not being transmitted. It's like somebody's calling you on the phone, if we still actually had corded phones.
Yeah.
Those come along and unplug the phone jack. And they might be like, send help, I'm bleeding, it hurts.
But they're still calling you.
They're still calling you, but
you're just...
it's not transmitting. Or it's transmitting very poorly. Whereas it might hurt a little bit, but it's not that major pain, right? No, it's not that it's not sending the signal, it's that the signal's not getting through, right? I mean, it's incredibly useful. Can you guys imagine doing any of the surgeries we do routinely without painkillers? If you ever want to watch something really interesting, Google or look on YouTube for Indian street dentists, and it's just some crusty old dude in the street in India, pulling people's teeth out with pliers and no painkillers. I mean, it's pretty crazy, right? And so, painkillers are really pretty good in the sense that it allows us to really do certain procedures without causing more damage than you need to. On the flip side, as we've seen in our society, the whole opioid addiction thing, it was a pretty big deal. It was a big deal, right? Okay, ethanol, I just want to point out, someone has said that if ethanol, alcohol, if that was invented today, would it be legal? And that's a really great question, and a lot of people argue probably not.
What's ethanol? Alcohol?
Alcohol. The type of alcohol humans consume on a regular basis. What do you think about that? Isn't that interesting? It's interesting to think of. If you take away all the societal context of it and just say, this substance does these things and it damages you in these ways, would we be like, I think it's a great idea and I want to drink some right now?
Yep.
Probably not. I mean, honestly, we probably would have reservations about totally embracing it. I mean, seriously. And I just think that's a good viewpoint to consider. That if it was discovered right now, would we be like, this is a great thing and stuff? And we probably would be like, not necessarily, right? Okay, moving around. We'll kind of finish up with this, take a quick glimpse at this, and then we'll go to the coloring sheet here. So, what about the different main physical divisions of your nervous system? Okay, you've got your central nervous system, which I'll just call the CNS, and the peripheral nervous system. When I say peripheral, what does that term mean? What's your peripheral vision?
Isn't it like the corner of your eye?
Your view out here on the sides, right? This is central, this is peripheral, right? Your central nervous system is your brain and spinal cord. The vast majority of all your neural tissue is there. The peripheral nervous system is all those little nerves that are going through the whole rest of your body that link that central nervous system to your muscles, your sensors throughout your body that link things. That's your peripheral nervous system, right? If you look at that nervous system, the central nervous system, brain and spinal cord. But let's talk about the peripheral first. The peripheral part is broken down into the part that sends signals to the brain versus the part that sends signals from the brain out. You don't use the same nerves to send and receive signals. It's different, right? So those different divisions are the afferent and the efferent, and it's like totally hard to keep those straight. You just kind of have to remind that or think about that. The efferent, the part that you're sending out from the brain, is then also really broken down into the somatic and autonomic division. That is the part that controls skeletal muscles and is voluntary. Remember how we talked how skeletal muscle, you get to choose to move it, versus the muscle that's in your intestines that moves stuff around. It's involuntary. Once you swallow something, you don't have any control over it until much later in the game, right? So those two divisions either involuntary regulate things like organs or voluntarily control things like moving around. And then that autonomic is further divided into your parasympathetic and sympathetic, which we'll get to tomorrow. I think will be appropriate. So kind of as the general diagram here, you've got your central nervous system. The central nervous system as a whole is broken down into just your brain and spinal cord. Once you get to the peripherals, you start thinking, okay, I'm sending signals, and I can send signals and control involuntary thing, or I can receive signals, and I can then get signals sent back in, whether it's your afferent or efferent divisions. Let's see if I can better. Let's pick up with the autonomic part tomorrow. We'll kind of go back over that. Okay, so we'll stop this here.